Hi there, and welcome back to the NeuroBytes video experiment series. In a previous video, you learned how interneurons work, and you experimented with inputs coming in on long and short dendrites. If you remember, compared to the short dendrites, the long dendrites required more inputs, or energy, for the postsynaptic neurons to fire an action potential. However, this can change as your brain learns a task. Real neurons are not like dumb wires that just pass a signal on. As you use them, they are constantly changing how they look and how they work. Let's experiment with how that works. Build a 3-neuron network with a touch sensor for input and 2 interneurons, the range is shown here. Interneuron A should be receiving input from the touch sensor on a short dendrite, and interneuron B should be receiving input on a long dendrite from interneuron A. When you click the touch sensor switch once, you should see that interneuron A flashes bright white, indicating an action potential, while the interneuron B LED turns red, indicating depolarization, but not enough to fire an action potential. Using a watch or clock if necessary, click the touch sensor switch approximately once per second. This is also called 1 Hz, a unit of frequency. How many clicks does it take to fire an action potential in interneuron B? As we practice a new task over and over, our brains get better at learning and remembering that skill, whether it's understanding new words or riding a bike. NeuroBytes interneurons can learn as well, in a similar way as the neurons in your brain. Hold down the side-mounted switch on interneuron B for approximately 1 second. If needed, you can turn the interneuron over to find the switch more easily. The LED should change to a magenta color, indicating that the interneuron is in memory mode. Now, when you click the touch sensor switch once per second, how many clicks does it take to produce a bright white flash, indicating an action potential, in interneuron B? In addition to changing the strength of existing synapses, neurons also capture memories by adding new synapses between neurons, and we can experiment with that too using NeuroBytes. Unplug and replug the battery pack on your 3 NeuroBytes circuit you just experimented with to reset its memory. Clicking the touch sensor switch once should fire an action potential in interneuron A, but not in interneuron B, just like you started with. Now, connect the second excitatory neurotransmitter cable between interneuron A and B on the other long dendrite. This is analogous to adding a new synapse between real neurons in your brain. What happens now when you click the touch sensor switch just once? Synapses between most real neurons have something called plasticity, which means that if a bunch of inputs happen within a short period of time, the postsynaptic neuron will capture more of that input energy and have a bigger response than it normally would with just 1 or 2 inputs. Essentially, the presynaptic neuron is telling the postsynaptic neuron that it's firing really fast because something important is happening farther upstream, and the postsynaptic neuron should remember that. When you first learned to multiply numbers or dribble a soccer ball, for instance, it was probably difficult because your neurons responsible for that skill hadn't formed stronger connections yet. With more practice, those existing synapses got stronger, and you also formed new synapses to capture that new knowledge. Scientists think that synapse plasticity is one of the main ways that we form memories in our brains that can last for hours, days, even a lifetime. If you practice enough and in the right way, no new skill is impossible to learn.